we are looking at Chapter 8 in the textbook, which covers metamorphism and metamorphic rocks. Metamorphic rocks are formed from a process called metamorphism, which is basically a combination of heat and pressure. These are the main concepts from Chapter 8, and the ones highlighted are the ones I will discuss today. So, distinguishing among the four agents that drive metamorphism, we'll look at foliated rocks in particular, and then descriptions of the metamorphic environments: contact metamorphism, hydrothermal metamorphism, subduction zone metamorphism, and regional metamorphism. First, let's do a quick review of the rock cycle. Metamorphic rocks are the final rock type that we will talk about in this class, and they are formed when heat and or pressure alter other pre-existing rocks that can be igneous, sedimentary, or metamorphic rocks. The parent rock of a metamorphic rock is known as a protolith. Here are some examples of metamorphic rocks and their protoliths. In this case, the parent rock, or protolith, is shale, which is a clastic sedimentary rock with loosely packed clay minerals. It undergoes heat and pressure at relatively low temperatures to form slate, a metamorphic rock with tightly packed chlorite and mica minerals. Here's another example of a metamorphic rock and its protolith. In this case, the parent rock is a granodiorite with randomly oriented minerals, and it's subjected to strong compressional forces and high temperatures and pressures to form a metamorphic rock called gneiss, where the minerals have lined up and then those bands of minerals have been folded. This diagram shows the types of heat and pressure that form all three rock types. As you can see in the diagram, sedimentary environments are generally cooler and at the surface, converted to sedimentary rock by fairly low pressures and low temperatures. Metamorphic rocks are characterized by being formed in increasingly hotter and higher pressure environments. A parent rock or protolith that undergoes higher and higher temperatures and pressures until it experiences melting is transformed back into an igneous rock. Let's look at the four agents of metamorphism as described in your textbook. They are heat, pressure, differential stress, and chemically active fluids or hydrothermal fluids. In all these conditions, heat is a common factor. Now let's talk about pressure and differential stress in particular. These two diagrams show the difference between confining pressure and differential stress. Confining pressure is when rock or strata are subjected to pressure from all sides and uniform heat. Differential stress occurs when the pressure is greater in one direction over another. This leads to the folding of the strata. We will discuss differential stress in more detail next week when we cover mountain building. Let's briefly look at the metamorphic environments that are discussed in your textbook. Regional metamorphism involves mostly pressure and often results from plate tectonic forces, including subduction. Contact metamorphism involves mostly heat and is often caused by a magma body upwelling beneath the surface and heating up the rocks around it. Hydrothermal metamorphism involves chemically active fluids which are usually at high temperatures, which is why it's called hydrothermal metamorphism. Subduction zone metamorphism is a type of metamorphism that occurs when one plate subducts underneath another, and the rocks and sediments are subjected to pressures and temperatures and convert to metamorphic rocks. This kind of metamorphism has led to the formation of many rocks in California. This diagram shows in terms of depth and pressure what conditions cause each of the types of metamorphic environments we've discussed. As you can see, the diagram shows hydrothermal metamorphism involving moderate and low temperatures but very low pressures, as well as contact metamorphism, which involves high temperature and very low pressures. Regional and subduction dome metamorphism can involve lower temperatures as well as higher temperatures, but they usually require fairly high pressures. Let's talk briefly about foliation and how it occurs in metamorphic rocks. In this diagram from your textbook, the protolith or parent rock has randomly aligned minerals before metamorphism, but when it's subjected to metamorphic pressures and temperatures, including differential stress, these minerals tend to line up in approximate banding or foliation. This is an example of banding, where mineral grains will line up in layers due to the differential pressures. This is an example of foliation where minerals not only align in layers, but also have undergone chemical changes to form different minerals. These new or metamorphic minerals are not the result of melting, but a result of change or transformation due to high pressures. This last part I want to discuss the concept of metamorphic grade or metamorphic zones. Metamorphic grade depends on the degree of temperature and pressure. So this diagram above, you can see that as pressure and temperature increase, the grade of metamorphism also increases. So lower temperatures and lower pressures tend to result in low-grade metamorphic rocks like slate if the parent rock is a shale, as it is in this case. Increasingly higher temperatures and pressures result in intermediate grade rocks such as schist, and high temperatures and pressures result in high grade rocks such as gneiss. Once a rock starts to partially melt, it becomes a migmatite, and once it's completely melted, it becomes an igneous rock. This diagram shows the relationship between the metamorphic zones, the metamorphic grade, and what are called index minerals, which are used to identify a metamorphic rock. In this diagram, the parent rock or protolith is shale. Under low-grade metamorphism, a slate or phyllite will be produced, and dominant minerals or index minerals include chlorite, muscovite, and biotite, all of which are micas. Metamorphic grade increases to an intermediate grade schist, and that's produced with the intermediate grade metamorphic temperature and pressure. And index minerals include biotite, but also garnets and starlites. Finally, under high-grade metamorphic conditions, the shale is transformed into gneiss, where the index minerals is. So that's all I have for today. Yeah, good luck.